Hello. I've been disconnected. Anyone hearing me?
Yes, I can hear you.
Yeah, we can hear you.
Okay,
but we can't hear the room though.
Ah, so maybe we need to wait some time.
Yeah.
Thank you.
Sure. They broke it all over again.
Yeah. Hi, Joel.
So hello, Bruno. Can you will the system let you share your slides again?
Yes. We got disconnected from the room at least.
Yep. It says your sharing is getting started. Waiting for it there. You need to back up to the beginning. We didn't hear any, the room didn't hear any of what you said.
Okay. So this is Ietf114 Spring Working Group. The session is being recorded, hopefully, both audio and video. This is the usual note well, so I'll skip it for sake of time. I'll try to be short. This is hybrid meetings. So if you are in person, you need to sign in using Miteco. And you need also to use Miteco to join the mic queue. And very importantly, you need to wear a mask anytime. And if you are remote, nothing changed. Please make sure your audio and video are switched off to avoid noise. And that's all. Minutes, they are collaborative. Shopping is the main minute taker, but you can help. Especially if you have comments, you can check your name and comments in live. This is the agenda for today. We have a full agenda, so we're already 20 minutes late. So please stick to your allocated time, which include both presentation and comments. Otherwise, we may cut your presentation. If people have comment on the agenda, you can go to the mic. In terms of document status, we have two documents submitted to ISG for publication. First is the pass segment in Mpls-based segment routing network. And second is integration of network service header and segment routing for service functions chaining. And finally, we have one new RFC, which is a segment routing policy architecture. It's an important milestone for Spring. So thank you to the authors, the working group, the Shepherd, the AD, and the ISG. And that's all for the chairs. We can now move to Christian for circuit style segment routing policies. Do we need to?
Before we start, just we've been asked to remind people that it is a requirement to have your masks on in the room. So if you haven't got them on, please do so. Thank you.
Okay.
Joel, do you want me to share the slides or it's okay for you?
I'll share the slides right now. Bruno, you need to release things and I will start sharing the slides.
Done.
Oops. Okay, our first presenter, yes, Christian, go ahead. I will give you have slide control.
Okay, thank you. Hello, everybody. This is Christian Schmutzer. I'm presenting as a representative of all the authors on the draft, and I will be talking about the circuit style segment routing policies. Sorry, I'm not sure if I can actually advance the slides.
What? I can't, I couldn't hear.
Maybe if you can do it for me.
I can take it. Okay, sorry.
We'll take control back and just prompt us when you need to change slides.
Sure. Okay.
Okay, go
So
ahead.
thanks. The motivation for circuit style segment routing policies is to allow operators to run a single network that not only carries what we call connectionless services, which is classical IP VPN services or layer 2 VPN services, in conjunction with more transport-oriented or connection-oriented point-to-point services, often called private lines or, in essence, if you will. Now, what circuit style segment routing policies are adding on is from a underlay transport, we're addressing additional requirements. First of all, to have traffic engineered paths which are persistent, meaning they are not changing because of traffic load or topology changes. They only shall change when the operator is requesting the paths to change. We're looking at strict bandwidth commitments and end-to-end path protection to achieve, very quick failure recovery, the famous sub 50 millisecond target, as well as restoration to handle multiple failures. And along with that, of course, path OEM, which is very important to understand the liveness of a path and understand when somebody needs to switch. Next slide. So how do we address those requirements, and what are the characteristics of circuit style segment routing policies? First of all, we have a centralized path computation element in the picture that is responsible to get the path requests. And part of the path request is, of course, the requested bandwidth. And the path computation element will make sure that we have bandwidth management for all the links. And this is important because in a segment routing network, you don't have any RSVP that normally would have done that job for us. We're forming bidirectional constructs which are co-routed by associating a forward and a reverse segment routing policy together. And the persistent paths we are creating by using a list of strict hops of unprotected adjacency sits. Unprotected adjacency sits are important because we have path protection and we don't want any TI-LFA, for example, to kick in. As mentioned, the path computation element shall not re-optimize the path only when the operator is requesting that. And that's a behavior that is commonly requested and known in the TDM world, aka Sonnet SDH or OTN. We are using multiple candidate paths. Now we're gonna program 2 of them to install a protection scheme, and there can be a third one if restoration is required as well. And STAMP is used to do loopback liveness detection or observation, if you will, and performance measurement. Next slide. How are we creating circuit style segment routing policies? Before we can create them, a few words on the topology. The topology is, every link has to be configured with unprotected adjacency sits, and they should be persistent across router reloads, which generally is done if you configure them manually and explicitly. The topology will be known by the PCE via IGP or BGPLS extensions. The path computation element will have the bandwidth configured for that is available for all the circuit style segment routing policies on each link. And our per hop behavior guarantees, assumed or required so that the provisioned bandwidth on the link can be at all time assured to be available for circuit style segment routing. The endpoints of the policy are acting as PCC and will delegate the path computation to the PCE. The draft is outlining a bunch of attributes or information that will be included in the candidate path request. Important is, for example, the C bit in the bidirectional association object to force co-routing. We also have some bits in the LSB A object to enforce no local protection, but there is a dedicated draft that will cover that. and it is being discussed in the PCE working group. And we're using multiple candidates as for protection. I mentioned that. The path computation element is responsible for configuring or computing working in the protect path in a disjoint manner, and we're using the disjoint association for that, and so on and so forth. Okay, next slide.
Next slide, John.
I'm going quite quick because I wanted to share the updates and the progress we made. We have done our first presentation at Ietf114 in the PC working group. We got quite a lot of input in the meeting as well as after that, and we received a lot of review comments which already got incorporated. The document changes are mostly around clarifying the role of the PCE and the stateful PCE. We added a section about how to deal with the maximum segment depth limitations that may arise, and we overall cleaned up or reshuffled the sections so that to get a better structure and readability of the draft. And speaking of the draft, one of the feedback was that the draft is probably more better suited in the Spring working group, and that's why we renamed the Spring working group and we're presenting it here. And final slide. We would like to get more comments and feedback. This is always welcome. We think that we got already the document in a pretty good state, and that's why we would suggest the working group to do an adoption call so that this draft may be adopted by this working group. Thank you very much.
Thanks, Christian. Nitsan, you were on the queue, but you dropped off. I don't know if you want to jump back on or whether you have a question or not. Okay, I'll assume not. Zengin, please go ahead. Oh, wait a minute. Nitsan, go ahead.
One issue is that I'm not sure about how do we ensure protection with resource allocation and bidirectional thing. I mean, it seems to be addressed, but I'm not sure exactly how. I'd appreciate any elaboration on those issues.
So maybe to cover the bidirectional. So we're going to use the bidirectional association to signal from both endpoints to the PC that those two SR policies belong together. And then it's the job of the PC to basically perform the path computation so that those both SR policies that are indicated to belong together are co-routed in a bidirectional, and co-routed manner, which I think is something that is already quite well defined with PSIP extensions. The protection, maybe I was going a little quick, right? So we have two candidate paths, the working and the protect. They will be signaled each as a request and each having a bandwidth requested as well. So when the PC is doing the computation and manages the allocations of all the path computation requests in the topology, it will allocate both the working and the protect bandwidth. So whenever we need to switch, the protect path is pre-programmed and already and has the bandwidth assumed or allocated from the PC perspective.
Robin, go ahead. Robin, please go ahead. He's coming.
Can you hear me?
Yes, we can hear you.
Okay. In fact, several years ago, the similar work like OEM protection and bidirectional SR paths have been taken into account. So the work of SR path segment has been developed. So in my opinion, I think this work has much relation with the existing path segment work. I wish the work can be taken into account in this draft and also can do some of the combination work with the path segment.
Yeah, I think this is this is a fair comment. Our draft, I think, is mostly focusing on the overall solution, how the co-routed and bidirectional computation and the paths are getting established. You know, establishing an end-to-end path segment as part of that. You know, I think fits in the picture. So we definitely can talk about how those two work items are aligning.
Okay.
Dhruv, please go ahead.
My one query is, like even in this presentation as well as in the draft, the PC is used extensively. Is
I can't
Dhruv,
hear
you
Drew.
got cut off there. Okay, we're going to have to move on in the interest of time because we were late starting. So let's move to the next presentation. And any other questions, please take to the mailing list.
Ryan, you're up. I've got your slides up.
Is it on? There we go.
Hello. Hi, my name is Gian Mishra. I'm with Verizon, and I will be presenting SR Pmtu for SR policy on behalf of the co-authors. Thank you. Next slide. So some history as to how this draft came about and came into the Spring Working Group. So during the adoption of draft PCE PSEP with Shiping, a need for a Spring document was requested and confirmed by both the PCE and Spring Workgroup chairs. So with that, during that discussion of the adoption, during that adoption call, an IDR document for SR policy path Mtu adoption. This topic had come up in April of 2020. A discussion was brought up by Ketan Tellur that the concept of path Mtu for SR policy and its applicability should be first defined in the Spring Working Group. Should be first defined in the Spring Working Group before we introduce the signaling aspect into BGP. So as a result of the PCMTU extension adoption call for PSEP path MTU extension was to maintain basically only protocol extensions. That was also as well requested for the IDR draft to just really maintain just the protocol extension details, while the SR policy path MTU definition and framework was to be developed in the Spring Working Group as a standards track document to ensure inter-vendor interoperability related to SR path MTU concepts and computation details. This topic came up as a critical issue to be addressed during the IDR workgroup adoption, as I mentioned, in 2020, and then the second time again during the PSEP extension for path MTU, due to the criticality of solving this topic and related to handling of fragmentation and fragmentation issues that could happen with an SR policy. Next slide.
You have a lot of slides and very few times.
Yep, thank you. So SR policy, so an overview here. So the motivation of handling the SR policy path MTU. So we got fragmentation avoidance by the SR head end to be aware of the SR path MTU associated with the SR policies, SR paths and policies. The ability to generate an ICM message at the head end if fragmentation is required, and then follow correct fragmentation procedures to ensure interoperability between implementations, and the ability for the SR policy as a path computation constraint to be added in a distributed model directly to the SR policy in CLI, or I'm in a centralized controller method with a PCSDN controller as a constraint that could be pushed down by the PCE to the head end source node. Next slide. So SR policy definition for SR policy, PMTU definition for SR policy. So basically a valid candidate path is selected as the active path, and once determined to be the best path for the SR policy, It could build a dynamic / explicit composite set of segment lists or composite candidate path container grouping of the SR policy. So with that definition, SRP MTU for a segment list is defined as the minimum link MTU of all the links in the path from the source to destination. SRP MTU for candidate path is the same as the SR policy, same as SRP MTU of a segment list for an explicit or dynamic is expressed as a set of segment lists, and the SRP MTU of the candidate path as defined as the minimum SRP MTU of all segment lists in the set. For composite is the minimum SRP MTU of all constituent SR policies of the composite candidate path. And finally, the SRP MTU on that SR policy is defined as the SRP MTU of the selected active candidate path. Next slide. So here just depicting kind of the SR policy for Pmtu framework. So in this example, we're showing an SDN controller. We have a path. So the SR piece, the centralized controller would basically push down via the PCE to PCC to the SR source node a constraint. So it would be an SR Pmtu constraint that we're pushing down from the controller to the head-end source node, and that's with the Bgpsr policy. So when that gets pushed, it would add that constraint into the policy to prevent fragmentation. As well as part of that framework, the link MTU collection would be done via Bgpls. Next slide. So the framework of SR policy for SR Pmtu for SR policy. So with that framework, the SR Pmtu path computation and how that would work for the variety of different paths. So a loose TE path would be the minimum SR Pmtu of all ECMPs between the two nodes between ingress source node and egress destination node SID along an SRT path. So that's basically the node SID ECMPs. So the next one is a strict TE path. So this here, it's a minimum link MTU of all links along the strict SRT path. And then a mixed is a minimum SR Pmtu of all ECMPs between the two node SIDs and the link MTU of all link MTU of all links along the path indicated in the adjacency SID. And then binding SID TE path is the SR Pmtu of the binding path is the same as the SR policy, except that it includes the associated encapsulation overhead for SRv6 with the outer IPv6 header and SRH and SR SID list that's pushed onto the stack. For TILFA, the SR Pmtu of the repair path at the PLR node to the merge point is computed by the controller, which updates the head end with the new SR Pmtu. So in that bypass loop, if there is a different MTU than the primary path, that path computation for the bypass loop is actually sent back to the head end node for the bypass loop. Next slide. So this shows an example of kind of how this would work. So this is an example of a SR policy for loose path with the node SID. So you have the node SID on the ingress and egress PE, and here we have an ECMP. So to keep in mind that we're looking at, so this could be an N-way ECMP. You have many ECMP that are there with the prefix SID / node SID. So now here it's the lowest lowest Pmtu of all the paths of all the ECMPs. So if you see the path from left to right, it's got an MTU of 2000, but then you see the bypass loop has an MTU of 1500. So as with the computation, it would be the lowest. So here the lowest would be that bypass loop 1500. So now here the controller would basically push down the constraint of 1500 down to the SR head end node for the SR policy. Next slide. So this example is a strict policy example with adjacency SIDs. And in this example, what I'm depicting here is, if you see, it's similar to the last slide. So in the path along from left to right, you see an MTU of 2000 with the adjacency SIDs. And then along the bypass loops, you see an MTU of 1500. So in this example, what we're trying to do is so normally the path MTU would take, as mentioned in the previous slide, the lowest lowest path MTU. So in this case, the lowest path MTU would be the bypass path, the triangle path along the bottom, 1500. So that would be standard computation when the path MTU is computed. So now what we're doing here is we want to take the higher MTU. So we want to take that 2000 path from that ingress PE to the egress PE. So in this case, what we're doing is we're actually pushing a constraint, a path MTU constraint of 1800 from the controller to the SR policy on the head end source node. And we're pushing down 1800. So since that is our constraint that we want as a minimum, and that actually forces that green line. So now we're actually, instead of taking the default path MTU using the lowest, which is the triangle path, now we're actually, with that new constraint, we're actually taking that green line path from left to right. Next slide. So this example is a loose, so it's similar topology. So we got left to right, we got 2000, and then we have the triangle path 1500 along the other path. And here is example of a mix. So you got prefix SID. So you take the prefix SID in the segment list. You have the prefix SID. So that's your first SID in the active SID in the SID list, and then you have an adjacency SID that you take along the path to get to the egress destination. So in this case, what would happen from left to right? You have the two-way ECMP here. Left to right, you got 2000, and then on the bottom triangle path, you got 1500. So it's the lowest of the path MTU along all the paths. In this case, it's 1500. So the controller would basically push down that constraint to 1500 down to the SR policy at the head end source node.
What slide do you want to finish up?
Okay, let's go down to the last. Do you have time for just one more? Go up one slide. Yeah, one more slide. Okay, thank you. So what I would like to ask the work group is if we could, if folks could review the draft, and we just want to get feedback. There are some critical components that we would like to get feedback from these Spring working group experts. The three topics that we bulleted with the with the authors, co-authors on as that we had discussed. The first one that we want to get feedback on from the Spring working group experts is the TI-LFA, SRPM2 TI-LFA computation and fragmentation caveats. So just to make sure we didn't miss anything, and want to make sure that we're really on target, and so really want to get feedback from the experts. The next one is the SRPM2 SRv6 source node encapsulation and fragmentation caveats. So, and the last one is SRPM2 binding SID path computation caveats. So much appreciated, and if and we'll take this to the work group mailing list, and I really appreciate the feedback.
Yeah, I'm really sorry we don't have time for questions, but we're really short of time this time, and we want to let things keep moving. So thank you very much, and the next presenter will be up in a moment.
Okay, thank you.
So this is the connection-oriented path in SRv6. I'm not sure who's presenting this. Zhangping, so go ahead.
And this slide is about the motivation. We think that the exact name should be the connection-oriented hop-by-hop switching path in the SR6. The hop-by-hop switching is just a way that traditional Mpls does on each node, in which the label is locally allocated and swapped on each node. As we know that SR6 packets can contain a whole or partial nodes to do the strict or loose source routing. Thus, fewer status on each node would be needed. However, if we need a strict T path in the network, we need to put each node seed in every packet header, which is not very convenient. Next page, please. And for the connection-oriented strict T path in SRv6, we have several options. First is we still put every node seed into the packet header. But if the path is long, the packet header will be large. Optionally, we can also compress the seed list. The second option, we can support both FRv6 and Mpls, but it is complicated. And this document mainly talks about the third option. We want to try to support hop-by-hop switching in SRv6 network. We think the benefits is that it is based on the uniform SRv6 network programming platform. And we also think that the platform can support many network characteristics and reduce number of protocols in the network. And we have two graphs. The first graph is about option 1, and the packet header perhaps need to contain each node seed. And in option 3, we perhaps have only one node seed in the packet header. We also add some explanation here. We think that currently we do not need to manage this kind of or connect-oriented paths in the network. Next page, please. For the forwarding on the data plan, we introduce a new set of seeds. On the data plan, it is easy to replace the label in Mpls with the seed in SVAR6. In this document, we call it endpoint x cop d function. It should be stored on each node and contain an argument similar to a label. This is a graph. We can see that on each node, the packet header, the destination in the packet header is changed. It's similar to the label swap, and we need these nodes to support the label mapping in a seed format. Next page, please. On the data plan, it is simple to introduce new seeds to replace the label in Mpls, but on the control plan, we also have two options. The first option, perhaps we can use a PCE server to connect to each node and communicate the labels for the path. And in the document, we also introduced another option. Is to simulate the procedure of SVT in Mpls by using new control plan seeds in SVAR6. We call it endpoint corp-c function, which is also needed to be supported on each node, and it perhaps contains an argument similar to a label. At this step, we think that the label 0 is special. It is used for the confirm the path. We have the graph, and the node 1 is the headend, and the node 5 is the endpoint. The first node 1 will send a packet containing the endpoint corp-c function with the label 0, and it is sent from 1, 2, 3, 4, 5 to confirm the path, and the node 5 will return a packet similar to the RESV in FZT. Next page, please. And we in this page we introduce the steps of establishing the path. The first step is we need the headend send a packet to node 1 to node 5, and it contains all the node seeds, and each downstream node will respond a label in the packet returned to the node 1, and they can establish this mapping table, but it is in the seed format. Next page, please. I think this is the last page, and thanks for listening. Welcome for comments. and contributions. Thank you. Any question?
Okay, any questions from the room? There's none on the queue. Okay, we're moving on then. Thank you.
Thank you.
Okay, go ahead, Yisong.
Hello.
Yeah, we can hear
me?
you. Please go ahead. Yep.
Okay, thank you. Hello, everyone. I'm Yisong Liu from China Mobile. Today, I will introduce NRPRD for the network slicing in SR6 segment. This is the first presentation of this draft. Next page, please.
Next slide.
Firstly, I will introduce the background, and as we know, network slicing partition a physical network into multiple isolated logical networks. A network slice associates with the specific network resources called the NRP, and NRP ID is used to identify the NRP during the packet forwarding, and it can be carried in the packet. And like the picture, the router can use the NRP ID to determine the NRP and forward the packet. Like the NRP ID equal to, the router will use the green line to forward the packet. So in this draft, we propose a method for the NRP ID in the SRA6 segment. So next page, please. Okay. This method to encoding the NRP ID in SRA6 segment. So in SRA6 seed, we have 3 parts of that locator function argument, and in the SRA6 TE mode, the segments of the intermediate endpoint along the SRA6 parts are usually the end or end.x type segment. So we can, and the argument field of this type segment are not defined. So we can use this field to carry the NRP ID. So the seed list in the RSRH, every segment can carry the same or different NRP IDs, which can arranged by the controller of the CLI. So next page, please. Because for the in the SRV6 parts, the SRV6 endpoint can look up the local seed table to extract the argument field to get the NRP ID. But in other nodes, like the non-SRV6 node, even the node cannot support the SRV6, only support the IPv6. So we need a table to get the NRP ID from the destination address. So we should create and look up the slice prefix table here. So with the static configuration mode or the dynamic advertising mode, that means from the controller or the CLI to the router or from the Bgpsr or the IGP to other nodes of the controller. And the protocol extensions will be provided in future versions or separate drafts. So this is the basic mechanism. So a slice prefix includes the prefix should be matched, and the second part and the encoding position in the segment, we can get where we can get the NRP ID. So next page, please. So this is the RSPT that we will build the local slice prefix table in every node along the SRA6 parse. For the head end of the SRA6, we will write the NRP ID into the segment, and for the intermediate nodes, we get the NRP ID from the destination address if the nodes are not the SRA6 endpoint. Like the example in the slide, for the P1 and the P3, they have a different slice prefix, and each prefix have the different position of the NRP ID, and if the destination address match the slice prefix, it can get the NRP ID position, and it can extract the NRP ID from the destination address. Okay, next page, please. This is the example for this mechanism. So we assume that we have two NRPs, and the NRP1 guarantees the 100 megabits bandwidth, and NRP2 guaranteeing 200 megabits bandwidth. So we dedicated the queues for every router to guaranteeing the bandwidth. So we have a SRA6 policy on the P1, including the segment for the P1 and seed and the P3 and seed. And for the P1 as the head end, it will determine the NRP, and it will carry the NRP ID2 to the P1 and the seed and the P3 and the seed, and it encapsulates the SRH and the IPv6 header. And the sorry, I'm not finished. And for the endpoint P1 and the P3, it can extract the NRP ID just from the local seed table. And for the P2, it's just a transient node. So it must look up the RSPT to get the NRP ID position to extract the NRP ID, and decide how to forward the packet with the queue. So that's all. We are seeking the feedback from the working group. Any questions, comments are welcome. Thank you.
I'll ask one question. This is Joel Halpern. As a participant, in looking at this material, I think I understand the general driver and actually like it, but the material needs to be much clearer about whether you are requiring strict paths, expecting strict paths, or expecting intermediate nodes which are not addressed to extract these arg bits from the current SID and handle them, which would be an unusual requirement. So we need to be very clear. I'm not telling you what the right answer is, but we need to be very clear about what we're doing.
Okay.
Any other questions on the queue?
Okay, thank you.
I didn't get my name on the list, but Darren Duke, Cisco Systems. Quick question: Is this a
hop by hop, every SR and non-SR node does this stuff?
That's what I was asking. Yeah.
Okay.
Non-SR6 node, it should get the NRP ID from the LSPT. So so thank you.
Okay, thanks, Yisun.
Okay.
John Wei, do you want to go ahead?
Hello, can you hear me?
Yes, we can.
Okay. Hello, everyone. My name is Jianwei Mao. I'm glad to introduce this new draft for you. Generalized Arguments of SRv6 segment. Next slide, please. Here is the background and motivation. In these years, some new features are created, include network slicing, IOAM, alternate marking, APN6, DNet, and so on. The instructions or commands of these new features can be processed at all nodes along an SR path or some endpoint of an SR path. That means the IPv6 hop-by-hop options header, the destination options header, or the SR-HTLV may be used to carry the instructions or commands. However, the usage of the options or TLVs will cause two issues. First, it will make the packet header longer. That will reduce transmission efficiency. And it will make the forwarding processing complex. That will affect forwarding performance. Besides, in the solution of SRv6 C-seeds compression with next flavor, if all the C-seed of the seed list can be put in the IPv6 destination address field of a packet, there is no SRH or the DOH, which is before the SRH, here in the packet after the compression. That means we will have no space to carry the instructions. Next slide, please. So in order to address these challenges, we propose this draft to use the arguments of the SRv6 seed to carry those instructions. Using the arguments, we will gain this benefit. First, we can reduce the transmission overhead because it will reduce the needed space of IPv6 extension header or SR-HTLV. Next, we can get better forwarding performance because the SRv6 arguments can be read and processed as a part of IPv6 address. That means it can avoid to process the extension header or SR-HTLV behind the basic IPv6 header. Finally, we may unify and simplify the packet processing because the instructions for the SRv6 and the new features can be put together in the arguments part. In addition, we noticed that there are several kinds of arguments for the SRv6 end seed and endo-X seed, which need to be compatible. For example, the SRv6 C-seed compression solution use arguments to carry multiple C-seeds, CL field, or both of them. Next slide, please. Okay, in this draft, we propose the generalized arguments. It makes the SRv6 arguments structured and generalized, and it allocates spaces to encode the instructions of multiple new features and SRv6 seed. This draft specifies two methods to use the generalized arguments. The first method is template. We configure a template to network devices, then the devices read and process the content of the arguments according to the template. For example, if the arguments has the total length of Z bits, we can define bit 0 to bit X stores the instructions of feature A, bit X to bit Y stores that of feature B, and bit Y to bit Z stores that of feature C. Next slide, please. The second method is called bitmap. This draft defines a bitmap structure in the arguments. It is used as an indicator. Each bit in the bitmap indicates whether the instructions of a specific feature exist and are valid. In this method, the generalized arguments have two possible formats, corresponding to MSB and LSB. Next slide, please. Moreover, this draft also considers how to interact with SRv6 CSID compression solution. As for the next flavor or the next and replace flavor, it is required to shift the C seed in the SRv6 seed. So the C seeds can be placed in the generalized arguments and need to be placed from the most significant bit. While shifting the multiple C seeds, the remaining parts of the generalized arguments should not be shifted. Next slide, please. So finally, we believe there are something to be discussed and clearly defined in the next step. For example, which bit in the bitmap corresponds to which feature, and what instructions or fields of the specific feature need to be carried in the generalized arguments, and how long is the space of arguments that we need to allocate for a specific feature. At the end, welcome to give us some advice online on the mailing list or join us to make some contributions. Many thanks. That's all. Thank you.
Thanks, Jianwei. I have a question myself as an individual contributor before I go to the queue. It's not obvious to me anyway what these features that you talk about are. You're kind of indicating that it's a feature, but presumably there's going to be more data. So for example, you talk about network slicing. Why do you need to indicate that feature when you're going to need more information than that to actually be able to do anything? You don't need to answer that now, but something to consider. The other thing to consider is potentially giving some example how the compression would actually work with this. So my concern would be for something like the next flavor, and if I've already used up all the bits for that, how I'm going to be able to do that. So just some things to consider. Kitan, do you want to go ahead?
Thanks for your comment. In the draft, we have defined a new flavor to indicate that argument part is needed to be processed as a generalized argument. It is named as a structured argument flavor now. This point is now shown in the slides for time reason. Thanks for your mention. And about how to interact with the SRv6 compression is shown in the above page.
Okay, Ketan, go ahead.
Okay. So I have a concern with this notion of generalized arguments because there isn't anything of that nature based for RFC 8986, the network programming. Whether SID has an argument or not, or whether it is valid or not, is determined by the SRv6 endpoint behavior definition of that SID. So if anyone wants to use arguments in a SID, there has to be a endpoint behavior definition which should precisely say what the arguments are or how it is to be processed. So I think maybe I'm missing something very fundamental or basic here.
Okay, thanks for your questions.
There isn't anything like a generalized arguments for that may be applicable for all SRv6 SIDs, basically.
Okay,
Thanks,
I guess
Ketan.
you are question about how to know to process the arguments as an generalized argument. In this draft, we don't define a new behavior for this. We define a flavor to identify this SRv6 seed is carried one generalized argument, and and it is needed to be parsed.
Sure. So you need to define, I mean, behavior flavor is like, I mean, I don't want to go into it, but you would need to define a new code point. Let me say that for SID behavior / flavor, that is going to use generalized arguments. They do not apply to existing ones that are defined and let's say today. We can discuss further on the list, perhaps, if you have any query.
Okay, thank you.
Greg, please go ahead.
Thank you. Greg Mirsky Erickson. I think that my comment is in continuation of Jim's comment, because it's not clear whether this argument it really defines the behavior or capability advertisement. What's not clear in particular is how DetNet is relevant to this. So basically, what you expect if this argument indicates the DetNet. Is it support of DetNet, and what else? Okay, thank you.
That's good.
Okay, thanks for your question. We just define a general space for the multiple or the many features. So the DetNet or the network slicing or the APN6 is just a example feature for this, and whether it is it is suitable to put a DetNet here, we can discuss further. Thank you.
Robin, please go ahead.
Okay, this is a quick reply about the questions. In fact, the arguments should be processed in the local node, but because the instruction to be processed by the specified segment, there can be multiple arguments for different features. So we need a template. We all need a structured arguments to be defined for this purpose. But we ask these comments. We should refine this draft to explain the use case more details. Okay.
Thanks, Robin. Okay, Fan, please go ahead.
Hi, this is Fan Yang from Huawei, and on behalf of the other co-authors, I present this redundancy policy for redundancy protection. Next, please. Yeah, here's some background of the redundancy protection. It is a generalized protection mechanism that and used in the context of the segment routing paradigm, and it replicates the service packet on the redundancy node. Shown in the figure, it replicates the service packet on the redundancy node and transmit the copies of the service packets from different destroyed paths, and transmit the first correct and eliminate the redundancy packet as the merging node. And to be clarified, the redundancy protection is triggered, is inspired by the DetNet packet replication, elimination, and ordering functions, but it is extended to provide protection functions to SR, to segment routing. And here mainly we use two draft to introduce this mechanism. The first draft was adopted by Spring last year, introduced the redundancy seed and merging seed in data plane, and to specify the endpoint behavior. And this draft introduced the redundancy policy in control plane to instruct the multiple redundancy forwarding paths from controller to the redundancy node. Next. So what is the redundancy policy? It is defined as a variant of the SR policy and with minimum changes. So it inherits the main structure and most attributes of the SR policy. And the function is to instruct the replication of the service packet and assign the multiple redundancy forwarding paths. So we specify it in there are actually, it works in two scenarios, and the scenarios shown in the two figures below. The main difference between the two scenarios is that whether the redundancy, whether the head end node of the SR domain is the redundancy node or not. So if the head end node is the redundancy node, it means that there's no necessary to use the redundancy seed at the head end, so that it determines whether we used redundancy seed or not. Next. In this picture, in this page that we used an example to explain the structure and the behaviors of the redundancy node. And in the figure on the right, there are three forwarding paths between the R node and M node. So we used the first two forwarding paths in blue as the redundancy node, as the redundancy path. So they are the seed list 1 and seed list 2 in the first candidate path CP1, and the third forwarding path in green is described in the second candidate path CP2 as the seed list 3. So in this redundancy policy that we introduce a new optional attribute at the candidate path level. So if we use the attribute is the flag. So we define one flag, the redundancy flag, to indicate the type of the candidate path is used for redundancy forwarding. So come back to the example here that if when the first candidate path CP1 is selected as the best valid candidate path for this redundancy policy, and this all the seed lists are used for, all the seed lists in this candidate path are used for the redundancy forwarding, not for the load balancing functions. So at the same time, the weight of the seed list is not applicable. And next. Yeah, as we've shown that in the scenarios that this redundancy policy can be optionally associated with the bounding seed, and actually the bounding seed should be the redundancy seed. So it is defined as optionally, yeah, as optional. Yeah, next, please. Here I list several draft and other actions that to make this function, make this mechanism complete. And yeah, I will also present the BGP and PCEP extensions in the following working group sessions. Next. Yeah, the next steps that we mainly want to have the discussion on the mailing list or on the meeting to refine the solution and also keep aligned with the SR policy if necessary, and further possible discussion on the alternative solutions. People may want to discuss whether why not use multiple candidate paths for the redundancy forwarding path. And we're happy to receive any comments and suggestions. And thank you.
Thank you, Fan. We have a couple of questions on the queue. Mike, please go ahead.
This is Mike from Cisco Systems. I just want to make a comment that I think it would be better if you replicate the packets across candidate paths rather than across segment lists. Because if you replicate it across the segment,
yeah,
use the load balancing.
Yeah, please.
of the SR policy. So you can't have load balancing anymore. And like you say, the weight is not applicable, right? So the weight is there for load balancing. So it's perfectly possible to do what you're saying if you replicate across the candidate paths rather than segment lists. That's all. Thanks.
Yeah, thank you for the comments. Actually, we think about which solution will be better or will be more suitable for different scenarios. But we can move to mailing list to have more discussion. Yeah.
Israel, please go ahead. Israel, please go ahead. You're on the queue.
Okay, can everyone hear me?
Yes, we can now. Yeah.
Okay.
Go ahead.
Yeah, Israel, AT&T. In the material you mentioned a binding set. You also mentioned something referred to as a redundancy binding set. However, what wasn't clear is if the redundancy binding set takes all of the semantics of a standard binding set, or if the standard binding set can also function as a redundancy set. Can you clarify that?
Yeah, the redundancy seed that we defined in the previous in the first draft, and it is we defined it as a variant of the bounding seed. I think it should take all the functions from all the semantics from the bounding seed, but add more functions like the replication of the packet to this new bounding seed. Yeah, but if you have any doubts about the semantics, if the semantics is correct or not, we can have further discussion. So far, I think it has the same.
Okay, thank you.
Greg, please
Yes.
go ahead.
Okay, Greg Mirsky, Ericsson. One question I have, and then probably a recommendation. So the merge function works on packet by packet basis or flow basis?
Yeah, the merging for the merging function that we define as a merging seed. So I suppose it should be percent packet by packet.
Okay. So in this case, it looks very similar to the PRIO functionality defined in the DetNet, so packet replication, elimination, and order preservation. And so I think that you might consider it presenting it and sharing with the DetNet working group at some point. Thank you.
Yeah, thank you. Actually, we have the previous discussion about the relationship between between here and the DetNet. So if the people still have the doubts or have not clarified, we will clarify it in future, both on the mailing list and the draft. Thank you.
Thank you, Fan. Yusong, you're up. Please go ahead.
Hi, thank you. Can you hear me well?
Yes, we can.
Thanks, Jim. Hi, this is Xuesong, and I will introduce our work about segment routing for enhanced DetNet. Next slide, please.
Next slide,
Joe. This page, I just want to show a very brief introduction to the audience. What is DetNet? Actually, based on the definition in RFC 8655, there are three key features for DetNet queues. One of them is bounded latency and bounded variation. That means there will be minimum and maximum end-to-end latency from source to destination, and also zero packet loss, which means there will be zero delay when packet switch when path switching. And also an upper bound on out of order packet delivery, and the reordering function will do its work to make the packet in order again. So all these features will be achieved by 3 technologies as resource allocation, service protection, and explicit routines. The existing technologies can be reused, or new functionalities or technologies can be introduced to achieve the standard queues functions or SLA guarantees. This document is to provide solutions for bounded latency with segment routing for DetNet. Next slide, please. Actually, as we all know, SR-Mpls and SR6 is able to provide explicit routine, which is also requested by DetNet. And for the convenience of presentation, I just take SR6 as an example, and SR-Mpls is very similar. With source routing, it could steer the DetNet flows go through the network according to an explicit routine by segment list in SRH, but only explicit routine is not enough for guaranteed bounded latency. So what's more? Next slide, please. What we are proposing is SRv6 extensions should be defined to provide explicit routine and bounded latency. The basic idea is very simple. If we just indicate explicit routine along a path, if we can guarantee the bounded latency for each hop inside the path, the end-to-end latency can be guaranteed. So here we just use network programming provided by SR6, which can give packet instructions in every node along the path to guarantee the bounded latency. So what kind of instructions is requested in this case? Next slide, please. Here, I just referred to another document. We have another document called bounded latency information, which is introduced for bounded latency function. The document will be presented in DetNet working group. The basic idea is very simple. We just want to avoid going into details of different hardware implementations for guaranteed bounded latency. We just define a concept, a general concept of bounded latency information, which have 8, we defined in existing version, 8 bounded latency information types. And we think cover most of the cases we have met the mechanisms to guarantee bounded latency. And also the bounded latency information value is specified value of BLI to provide guidance for packet processing with the meaning of a particular BLI type, as I have mentioned, one of the 8 type in the table in the right hand. So the information pair BLI type and the BLI value should be indicated by SRv6 data plan to provide bounded latency. Next slide, please. I noticed Greg is in the queue. Do you want to ask now or after I finish the presentation?
Go ahead, Greg.
Okay, thank you. Greg Mirsky-Erickson. So can you clarify when you say guarantee, what particular technique you use to guarantee the latency or jitter or any performance metric value?
I think here we try to go align with the definition in DetNet, because DetNet, in DetNet queues, the terminologies of guarantee, in my understanding, is to provide an expected bounded latency, which means that we know the maximum bandwidth and the minimum bandwidth from the source to the destination.
You're right. So in DetNet, I think that there is no discussion of guarantee. The mechanisms discussed, TSN or pre-auth, improve or reduce certain behaviors, but they provide no guarantee.
Actually, if there is no guarantee,
only time division multiplexing can provide the guarantee. In the packet multiplexing, I believe that we have no guarantees.
if there is no guarantee, there is no meaning to mention that we can expect a particular value of the maximum or minimum of the latency.
I believe the detailed definitions of these are said to be DetNet. This clearly will not advance until the dependent DetNet stuff is adopted. And so we'll leave it to DetNet to debate the exact way to describe these various properties because it's their space. The only question for Spring would be how to indicate DetNet properties in a Spring segment list. Okay.
Yes, I agree.
You may continue.
Yeah, thank you, Joy. I agree. I think the definition of the terminology or the meaning of the terminology, we can leave it to DetNet. And this page, I just want to summarize the ideas from the previous slides. Bounded latency information is used to guide forwarding in a network device, which could be initiated in SRv6 data plan, for example, also similar as Mpls SR data plan. With the characteristics of segment routing, the bounded latency information could be coupled with the explicit path to provide the latency guarantee in each hop, or both it can be node or adjacency indicated by the segment list. In order to achieve this, in this document, we introduced two new variations of end.x seed. They are defined for DetNet bounded latency, which are called end.x BL and end.x BLI. The main difference of these two seeds is whether to carry BLI explicitly in the encapsulation. For end.x BL seed, it has two meanings. One is to identify an interface or link, just like the normal adjacency seed. The second meaning is to identify the information pair of BLI type and the BLI value on the interface or link to guarantee bounded latency. So there will be multiple end.x BL seeds for one adjacency in order to differentiate different BLI type and the BLI value to guide the packet forwarding. And another variation is end.x BLI seed. It also has two meanings. The first one is to identify interface or link as the normal adjacency seed, and the second is to identify the BLI type to guarantee bounded latency. In this case, the BLI value will be carried in the encapsulation of the SRv6 packet. Now, there are three possible options have already been defined in this document. The first one is the arguments in the end.x BLI seed, and the second one is SRH-TLV for BLI, which will be used together with end.x BLI seed. And
we just lost you, Song. We just lost you briefly there, Song.
how about
okay,
now?
You're back. Go ahead.
Okay, thank you. I just finished. There are three possible options to carrying the BLI information value. And what is the next? We would like to collect the comments from Spring and the DetNet, like Joy has already mentioned. Maybe the definition of mechanisms should be left to DetNet, but how to make SRv6 and SRMPS to support this function should be left to Spring. And we would like to collect feedback from both working group. And also, we would like to seek for cooperations with people who are interested in this work. Thank you.
Thank you. Any questions from the room? There's no questions on the queue. Okay, we'll move on to the next presentation. Okay, Hal Lee, please go ahead.
Hear me? Can you hear me?
Yes, we can.
Okay, first page, please. Hi, this is Yiho from H3C, and I'm going to present these two drafts on behalf of the authors. These two drafts are all about the extension of Bgpsr policy. This page is the motivation for segment list identifier. We know the draft segment routing T policy defined as a policy to distribute as a policy to the headend node. There are policy name and candidate path name to identify the policy and candidate path respectively. For segment list, there is no ID or name in SR policy. So in some scenarios, it is inconvenient to do some process about segment list. One case is reporting static from headend node to controller. Normally, headend can collect forwarding static count based on segment list. One report the count to controller. Headend has to report static with the whole segment list, and the controller has to compile the seed one by one to identify which segment list is reported. And another case is distributing configuration. It is from controller to headend node. In addition to distributing policy through BGP as a policy, the controller also distributes configuration through netconf. The procedure is similar. The whole segment list has to be carried. In these cases, identifier or segment list may be helpful. Next slide, please. Yes, this is okay. Thanks. This draft hopes to add the segment list identifier in Bgpsr policy. The identifier could be ID or a name. Next slide. This page, two subtailways are defined. The left subtailway specifies identifier of the segment list by a 4-octet number. The right subtailway specifies the identifier of a segment list by a symbologic name. These two subtailways are optional, and it must not appear more than once inside the segment list subtailway. Maybe just need to keep one of them. We can update the draft according to feedback of the working group. Next slide. Yeah, and this is another draft about the headend behavior. We know there are multiple ways to steer packet flow into SRv6 policy. For binding seed steering, multiple behavior have been defined. The multiple SRv6 binding seed with different behavior could be encoded in the same SRv6 policy. The headend perform corresponding behavior associated with SRv6 binding seed. But for other steering way, the headend behavior is not specified by Bgpsr policy. Next page.
Hao Li, before you move on, Chung Li, do you want to ask your question? Because I presume it's on the previous
okay.
document that was described. So Chung Li, please go ahead.
Yeah, thank you, Jim. Chung Li from Huawei. So, firstly, it's really happy to see the people also thinking in the similar way. Actually, we have some draft to propose some like segment list ID identifier or path segment, something like this already. So we can discuss further to see how to cooperate together to avoid redundant draft in the ITF. Thank you.
Okay, thanks, Jim.
And Ketan, is your question? Do you want to take your question now, or is it on this this other document here?
This is over.
Go ahead then. Go ahead, Ketan.
Wait for the presentation to get over.
Okay, fine. Hao Li, please continue.
Okay, please, next slide, please. Yeah, this draft hopes to add hand behavior in Bgpsr policy, and the hand behavior is only for SRv6. Next slide, please. Okay, the two sub-TLV are defined for distributing SRv6 policy. The left sub-TLV specify the behavior for layer 3 traffic for behavior as defined. The right sub-TLV specify the behavior for layer 2 traffic, and two behavior are defined. These two sub-TLV are optional and must not appear more than once in the SR policy encoding. Yeah, next slide. Okay, that's all.
Okay, so couple of clarification and one question. The clarification is that the SR policy Yang model does have a name for a segment list, and I think that should normally be sufficient. So I would suggest that that's something to be looked at. The second point is there were feedback here on the Bgpsr policy, and I would much rather prefer, and I'm speaking as a co-author there, I would much rather prefer that such feedback is given on the IDR list, so that we still have a chance to make any changes or address any comments rather than bringing new documents. So I believe that we have the necessary things there to address this and BCID behaviors. But if you think that it is not, please comment on the IDR list. Thank you.
Thank you.
Okay, thank you. Just pulling up the next presentation. Okay, Shraddha, please go ahead.
Hello, can you hear me?
Yes, we can.
Okay, this is Shraddha Hegde from Juniper Networks. Myself, along with Dhananjay, will be presenting this draft on problem statement for inter-domain intent-aware routing using color. Next slide, please. So some background on this draft. So we had a seamless SR problem statement in Spring working group and another draft BGP card problem statement in BEST working group. So as the problem statement documents were addressing the same use cases, the chairs suggested us to merge this document. So the authors from a subset of authors from both the draft worked to produce a merged document. So this is the first version of the merged document that we have posted. Next slide, please.
Go ahead. We're not hearing Shraddha. DJ, are you there?
Hey, hey, Jim. Can you hear me?
Yeah, do you want to take over because we're not hearing Shraddha here?
Okay, sure. So yeah, so the problem statement is focused on defining requirements and of course use cases for building intent-aware paths across multiple domains, and again focused on a distributed routing solution, primarily on BGP, given BGP is the inter-domain protocol in many of these networks that are being targeted. Of course, the requirements are general, so they could apply to other solutions as well. Next slide, please. Next slide. Yeah, thanks. So in general, why focus on BGP? clearly today BGP-LU is used in many seamless Mpls as well as some multi-AS deployments. So operators have operational familiarity. So some of them expect an incremental solution that they can deploy in lieu of BGP-LU. There is an expectation that with the familiarity with BGP, it would support a higher scale than what they are deployed currently, and there is the familiarity with the the sort of the trust model when if you have to go across different BGP domains, mostly in terms of peering policies. Next slide, please. So, as Shraddha said, this is a merged document. So what we managed to do is put together some sections that with the content that we would like to see. So some of these sections, they're broadly divided into two areas. One is look at some of the typical deployment scenarios, explain some of the use cases. So that's like the first set of sections. Next slide, please. And then given that there is already a set of solutions, including the SRT solution that's been standardized and deployed by the Spring Working Group and supported by multiple implementations. There is a section that defines an intent-aware routing framework, introducing some of the base constructs, the concepts, and how existing solutions work. So this is meant to be used as a reference for some of the detailed requirements in the subsequent sections. Next slide, please. Then we go into some details, in terms of the technical requirements. Again, it's broken up into different categories. There's a section on the intent requirements. Currently, what we have are the transport network requirements specified. In general, the sections that you see underlined are ones that are placeholders, specifically the VPN layer intent requirements, the OAM requirements, as well as the multicast intent requirements. The co-authors and editors, have not yet managed to discuss and review the content in those sections. So, but we will address them in subsequent versions. In terms of the other requirements, we have the steering requirements. We have deployment requirements that go into different topologies, different transport types that are that need to be supported. A variety of interworking and color mapping scenarios are also described. And then we have scalability as section, network availability requirements, and finally, given that the primary target here is BGP, there is a section on BGP protocol requirements as well. Next slide, please. Yeah, so I don't know how much time we have. I mean, in general, what we've done with the network intent requirements, this is not an exhaustive list, but there's a number of commonly seen scenarios. So we've provided a description of those scenarios with reference topologies and flows. The idea being to be used as a reference for various solutions. Next slide, please. Again, when it comes to steering, we start with the baseline that existing solutions like SRT support. We added some more detail on fallback in terms of things like ordered fallback across multiple intents, the granularity of fallback schemes, and so on. And of course, the requirement for steering to be supported for all services. Next slide, please. Again, in terms of scalability, we provided some data on the target scale, and then some analysis on what that entails for existing designs, what are some of the constraints that need to be taken into account. And then in terms of requirements, we focus on two broad requirements. One is to scale the Mpls data plane, the need for hierarchy, and then also to reduce the control plane state as well as data plane state, the need for a subscription based pull model. Next slide, please. So we have gotten some good feedback already after publishing this first the 0.0 version. We do request more folks to review and provide their comments. Thanks to the ones who've already done that, and thanks also to Joel and Jotaro for guiding the merge effort. Given the time we spent on this and the the content and the quality of the document, we think it's in a good shape to be adopted by the working group. So we request the working group to do that. Thank you.
Thanks, DJ. You mentioned about working group adoption. So if the document gets adopted, then the chairs obviously want to see that front page cleaned up, preferably with editors and everybody else moved into contributors. But I'm sure you're aware of that. But the sooner that's done, obviously, the better. So if you could take that to your co-authors, that would be
sounds good.
Thankful from the chairs.
The other thing I will just remind all the participants is that the technical work on how the heck to do whatever it is that meets these requirements is in the IDR working group, not the Spring working group. Please do go to the IDR working group and participate in the discussions there. Okay, we'll go on to the next presentation, which I need to briefly introduce. As soon as I can convince my machine to let me. Okay, we are pressed for time. This is a brief presentation on one of the proposals for encoding changes to the MPLS header. This is an active topic being discussed in the MPLS working group. There are multiple proposals. What we have here is one of them to give you an idea of what's going on in this space.
Hi everyone, my name is Rakesh Gandhi and presenting the M&A encoding for everything that's about the bottom of the stack on behalf of the authors listed. And next slide, please. So agenda, we won't go through a lot of details about the encoding and bits and pieces, but we'll show the salient features of the encoding. Next slide, please. So many thanks to the open design team between Pulse and .NET and MPLS. There's a lot of work done there for the requirements, framework, and use cases. So this is basically leveraging the work to provide the encoding formats. Next slide, please. So basically in the encoding, we need two things. One is the present indicators. So there is an M&A label, we call it the indicator for the network action substack. And the flags that says there is a in-stack or post-stack. And basically, the second part is the network actions, the flags or opcodes. This says this action needs to be performed. Next slide, please. So the encoding, basically, there is a label. This is a base special purpose label. That's an indicator. And the next LSC has the encoding flags in the TC and TTL fields that has a length and the present indicators. And there is a flag-based network action defined in the second LSC. Next slide, please. So this is more details about the flag-based network actions. Next slide, please. And this one is an encoding that shows the opcode-based network actions. It can contain the ancillary data that is used to execute the network actions associated with the opcode. There are other fields like the scope and the length, also part of the same LSC. So this makes it hardware parser friendly. Next slide, please. So this is just an example of if network action is to be performed, a flag is assigned by INA that this flag is to do that network action. Next slide, please. If there are more than 19 flags required, it can be easily extended. Next slide, please. This is the one where opcode 10 is assigned to perform some action with its data. And next slide, please. So this is an example where if you need to have more than 20 bits of data for that opcode, it can be easily extended as well. Next slide, please. It can be encoded with the flag-based and the opcode-based network actions in the same network substack in the same packet. Next slide, please. Again, it's flexible enough to carry multiple opcode-based network actions, and NCAP node can put the network actions in certain desired order. This is an important characteristic of the encoding. Next slide, please. So the encoding is backwards compatible. Obviously, the capability needs to be signaled that node is capable of M&A processing. The ACMP is not adversely affected. It does not alias with an existing reserve label, so it will not cause an issue in a legacy network. The penalty mode TTL propagation will not corrupt the M&A because we're leaving the TTL and TC fields as is. And it can coexist with the GSCH and other current encodings. Next slide, please. So it is aligned with the M&A framework and requirements for in-stack and post-stack. It's flexible. You can put the action in the desired order. It can be easily extended for various use cases. We have worked with multiple vendors. The encoding is hardware parser friendly because of the fact that the opcode, the data, the scope, the flags, the length, everything is in one LSC. So it can execute the instruction quite easily in hardware. It is MSD efficient because you can take advantage of the various encoding formats. Backwards compatible, we make sure it's backwards compatible, and ECMP friendly as well. Next slide, please. So welcome your comments and feedbacks. There is very strong interest from multiple vendors and operators, and we have requested working group adoption in the Mpls working group. Thank you.
Thank you very much. My thanks to all of the presenters who were expeditious and helped us make up the time we lost to do technical issues. And the fact we've even squeezed in a few comments. I really prefer discussion, but we have what we have. So thank you very much for your time. We'll see you on the mailing list where the work actually gets done. Please engage. I'll take a minute and then I'll be walking around.